I said it needs you need to have the knowledge of molecular descriptors. Okay, because whatever models you are going to create, the quality of your model, it is going to be dependent on this descriptors. So we had talked about some of the molecular descriptor. One of them was partition coefficient, and when we saw this, we saw it like something about the partitioning between a polar solvent and a non-polar solvent. The polar solvent was your water, the non-polar was the N-octanol. Okay, so that is, it was like one of the type of partition coefficient. So we said when P, it is resembling the partitioning. So the concentration in the octanol phase to the concentration in the water phase. So something it was talking about more amount of, if hydrophobicity is there, so more log P will be there. If it is close, log P is 0, means it is equally partitioned in between the both in both phases. If it is less than 0, means it is more hydrophilic. Okay. So last time I said whether only the high log P value should be your necessary criteria for it to be a good drug candidate. So as I mentioned earlier, that most of the time the pocket is hydrophobic. So you need to have some amount of hydrophobicity so that a pharmaceutical compound should bind to the particular receptor. But we understood that this is not the only criteria. Because even though you can see that many of the pharmaceutical compounds are having the value greater than 0 based on this data of 3000 compound, but somewhere you can see it should also have some amount of hydrophilicity. Means it has been mentioned that log P value should not be greater than 5.0, and values between 2 to 3 it is considered optimized for something called as ADME. So this ADME we will try to understand today. So I mentioned that everything should be optimized and why it is necessary. So it is mentioned that along with binding, so many other things a pharmaceutical compound should do. So that we are trying to understand. So here, like if we know which descriptors to choose, because we cannot choose all the descriptors from the thing, so otherwise our calculation will be super tedious. So we are going to choose the descriptors on which our modeling will be dependent on, the accuracy will be depending on a lot. So many of the descriptor I talked about. So one of them is topological indices that I said I will explain to you next time. So this is one of the example of a topological index. Like I said, partition in coefficient was one of your physico-chemical descriptors. In the same way, there are so many other descriptors. So topological indices, what does it mean? Like this is one of the example, like based on the molecular structure, what you can represent on the computer, you can calculate some descriptors, like some numbers you can calculate. So there are so many indexes like that. So one of them is Wiener index. So like here you can define it like it is considered as sum of lengths of shortest paths between all pairs of vertices in the chemical graph representing non-hydrogen atoms in the molecule. Okay. What is the meaning of this? If you just look this particular example, you will quickly understand. Like for example, here the N-butane molecule is considered an isobutane, and both of them have a Wiener index different. The N-butane is having 10 and the isobutane molecule is having 9. So here, like if you are considering the N-butane molecule, so you have to consider the sum of the lengths of shortest paths between all pairs of vertices. To understand it more clearly, just consider that N-butane has three pairs of vertices at distance 1 from each other. Means there is some calculation that is being shown by 3 into 1. Okay. Then there are two pairs of distance 2 and one pair at distance 3. So 2 into 2, 1 into 3. So this is totally, it becomes 10. Now what is this? 3 into 1 means you can consider like all these three pairs of vertices at distance 1 means this is the vertex, this is the vertex. So if you are, this is 1, 2 and 3. So this is, they are counting as 3 into 1. Then the same thing, the sum of the pairs from the vertices. So this is also considered as one pair, and this is as another pair. When they are considering the factor of like these two together and then these two together, so that is becoming 2 into 2, and finally all together. So 1 into 3. The entire all the vertices one pair at distance 3. So this will become 1 into 3. So this become 10. If you compare it with isobutane, so you can see that it will be having 3 into 1 from here to here, here to here, here to here, and 3 into 2. Like this would be 1, this would be another, and this would be another. But there is no such thing as 1 into 3 like what N-butane had. So this is something like just based on their structural representation, you can evaluate some number and you can try to relate it with some of the activity or property of the compound. Okay. So here they have given the example like it has been proved in the literature that indexes like Pioneer indexes, they are very closely related with the boiling points of alkane. Like the index are proportional to the boiling points. And it has been also shown like what method we are going to study QSAR, that the binary index can be also uh, the binary index can be also correlated with the other parameters such as critical point, density, surface tension, and viscosity. Okay, and also the van der Waals surface area of the molecule. So in the same way, like so many of the parameters can be evaluated and we can do our QSR modeling. Okay. So this is one table, it has been given to you, like what you can do with this molecular descriptor. You want to always, in the methods like QSAR, you have the structure and that you want to relate to the activity. So suppose the activity value for 7 compounds you have determined experimentally. So these all this for 7 compound the values are given to you, and these molecular descriptors for them, like for example hydrophobicity or molar refractivity, you can calculate also through the experiment. Okay, and based on this you can come up with the model. And for compound number 8, you can get the values of hydrophobicity using your chemical informatics technique, and using this model which you have also developed using the regression technique. So this actually can be utilized for predicting the activity of the compound number 8, 9, and so many of them. So based on this, you can come to know whether whatever activity value you are interested, if you are looking for higher activity value, so which of the compound is having the highest possible activity value, so that you will consider using this method that this is the best compound. So I said we need to find out, like if I say, okay, go and find out like which for this particular disease you want to generate some model. You have some initial database, like how are the activity values, this you have already got, but now your duty is to choose the particular molecular descriptors. Now this will come from the idea of what a particular disease is, what is exactly happening within your body, like the structure of the particular receptor and so many other aspects, like what particular disease it is, in which part of the body that particular receptor lies. So all these things needs to be understood. So many time what is exactly going on within your body, you need to understand so that you can choose those particular descriptors. Again, I'm saying the better the descriptors you are having, so better the QSR modeling will be. Okay. So there are so many softwares, like this is one of the software like ADMET predictor. So here ADME, I'm going to mention T is something related to toxicity that I'm not going to discuss much. But this kind of property, just by screening your databases, you can find out a lot many of these things. And this is the one of the commercial package. So I said later on in the part of the course you are going to do some mini project, so these kind of studies you will be doing. But I would suggest like never download any commercial package, any pirated version or something. Whatever you are going to do even for your mini project, just always try to use some of the freeware softwares. Okay. So what is this ADM? Okay. So consider that I said for you what is important, the activity value of a pharmaceutical compound, and this activity, it can be considered either as a beneficial things or a adverse thing. Okay, and for a drug to be effective, it should not be only active against the target, but they say it should also possess the appropriate ADME properties. Means it should not be active only against the target, means it should not be just binding to the particular receptor cavity, but along with that it should be also having these proper ADME properties. If it is not satisfying, so in the earlier stages of your screening you can just remove the pharmaceutical compounds, even though later on you find out that it is binding to the target properly. Because if it is not satisfying the ADME properties, so then it is very difficult for you to get it approved from the FDA. These people have some other ways so that they can even incorporate certain thing. Like I will give you some example. Even though when it is not satisfying this criteria, still sometimes by using some other methodologies, you can get it approved. But this is generally the criteria. So what is this ADME? I mentioned to you absorption, distribution, metabolism, and excretion. These are the four things that you can consider anything you are taking inside your body. So ultimately it has to be absorbed, distributed, then metabolism, and then excretion should happen. So entering, moving through the body, then metabolism is something that whatever you are taking within the body, it is going to most probably change with your body. So those aspects are also important in many cases. And in the final case, the way of living outside the body. So many times, how any pharmaceutical drug, whatever is getting approved, how it is going to deliver it in your body, and what is going to be its ultimate fate. All these things needs to be understood properly so as to decide which molecular descriptor should be considered for your study. So the first thing, the absorption, you can consider it is the movement from the site of administration into the bloodstream. Okay, I said in this lecture some biology will definitely come, because as you want to find out which descriptors are important, so you need to understand some processes within your body. Okay. So you can consider whatever way you are taking the pharmaceutical drug, in the way of tablet or injection or any other way. So from there, how it is entering into the bloodstream, that is the absorption. Okay, it is not the distribution throughout your body, that is the second step, but just how it is entering into the bloodstream. So they say any pharmaceutical compound, it should eventually, it needs to find and go to that particular receptor where it is going to act upon. But this is the just first step, that you have taken the drug and it is going to the bloodstream. So first, whenever this drug is going into the bloodstream, it has to pass through so many surfaces. Like for example, your digestive tract would be one of the surfaces where this drug should act upon. So you can consider like smaller molecules, are going to diffuse more rapidly, and if you consider larger molecules, they are going to diffuse slowly. So here you can consider, this gives us some idea, like if the pharmaceutical compounds are slower, their diffusion or something, the rate of action will be faster, whereas so if it is taken after the meal, they say the action of the drug can be noticed much more quickly. So in that cases, the doctor can prescribe it after the meal. So many times you can consider that pharmaceutical drug molecule, what kind of properties it is having, whether the acidic properties or basic properties, like whether it is having the uh, H plus donor groups or H plus acceptor groups. So this is also important. So whenever you are going to have some pharmaceutical drug developed for a particular purpose, so you might be interested that which particular descriptor is more useful to you. So that should be definitely in your modeling, so that you should be able to get the correct amount of activity value. So many times this hydrogen donor group or hydrogen acceptor group, how many numbers are there within a particular molecular structure, this is also calculated from the software, and this is considered as a part of the ADME process.
Hello, sir.
Yes.
Sir, you weren't audible in between.
Uh, which slide? This one?
Sir, in the first slide of absorption. No, sir. The before this one. So here, after you covered the third point. No, sir. The next one. The first slide of absorption. Yes, sir. This one.
Okay. This one you are
After you
saying?
covered. Yes, sir.
Yeah.
No,
I said here
sir, the previous one.
previous. This one? This
Yeah,
one?
this one, sir.
Okay.
Yes, sir, this slide.
Okay. I said we are trying to understand what are the roles of molecular descriptors. We cannot model everything by choosing each and every descriptor. So we are trying to understand which molecular descriptor to consider. So for that, I said ADME is important thing. So here you should consider like uh, the first step is that whenever you are administering any drug in the form of like tablet or injection or any other, like even there are so many other ways. So from that, how it is entering the bloodstream, that is important. So this is like one of the point. Like small molecules is diffuses very rapidly, whereas larger molecules diffuse like very slowly. So you can consider that molecular mass as one of the descriptors you should consider. So many times in the screening purposes, this is the important factor, so that your diffusion should be also faster. So you will not consider any pharmaceutical drug having the higher molecular mass. In the same way, I said the hydrogen donor groups or hydrogen acceptor groups, how many numbers are there within a particular structure, even that is also important, and you should also calculate it before you do any kind of screening. In the same way, I said partition coefficient is important. Like you can consider so many times the absorption to happen, the uh, the the higher hydrophobic compounds or lipophilic compounds, they create issues, but you should consider that they should be water soluble. They should be having some group which should make them water soluble. So if they are totally hydrophobic, so they are not going to get absorbed, so that is going to create problems. But there are so many of the pharmaceutical compounds which are amphipathic in nature, like amphiphilic, so they do not have any problem in getting absorbed. Like amphiphilic means having both hydrophobic and hydrophilic group. So even though it is having the hydrophobic group, but hydrophilic group will make it water soluble. So transportation properties will be easier. So whenever you are saying this partition coefficient, we have understood earlier that it should be, even though the having higher side of hydrophobicity, more lofty, but it should not be too high. So this you should consider as one of the molecular descriptors. Now, there are considerable studies. I said there are so many compounds which are hydrophobic. So they say 40% of the approved drug by the FDA, they are poorly water soluble, like very hydrophobic, and even so many of the developmental pipeline drugs which are not yet approved, even they are having a lot of hydrophobic properties. So I said ADME criteria is important. So can you simply discard the molecule which are going to show that they are having good activity? So no, there are so many drug delivery strategies. Like people have proposed so many different ways so that they can be also used. So one of the very like scientific approaches I will discuss later, but some of the things what people do, like if you are not able to give it by a simple tablet, like generally the drugs which do absorb very poorly, so then they are administered by other ways. Like there are different ways of administration. Like for example, normally you take by oral way, but like in the form of some injection, intramuscular way, subcutaneous way, or even there are some chemotherapy drugs which are taken intravenously, or so many times there are some topical patches like on the skin itself. You can see even if there are some like pain in a particular part of the body, if you want to remove, some people they wear a skin patch. Okay, so they release it like effectively, so that you don't need to have always use the oral way. So there are different ways how you can take the thing. So if there are very poorly soluble compounds, so you need to take it in a different way. So that was related to some absorption stuff. Then distribution, whatever drug molecule has came into the bloodstream, now that has to move throughout your body, and that after the movement, wherever it has to release and bind to the particular receptor, it should do that. So many times this distribution is important that it should happen at like rapidly. You can see the average circulation time of your blood is just 1 minute. So you can consider from one part it is going and coming back in just this small amount of time. So your pharmaceutical drug should also be able to follow that. Okay, but different compounds act in a different way because there are going to be interactions of the pharmaceutical drugs with the different components within the blood. So you can consider that whenever the drug is moving into this bloodstream, it has to go into some part which is called as body tissues. Okay, so what are these body tissues? This can be considered as something intermediate to what? Cells and a complete organ. Just for example, you can consider this, there are so many of these tissues. Suppose there are these nervous tissues. So your entire brain you can consider as a complete organ, and within your brain there are small cells. So the tissue is something which is intermediate. So the part which is made up of these so many cells, one particular part can define that particular region. So you can consider tissue is something the intermediate level where actually your pharmaceutical molecule ultimately try to reach, and from there it try to enter into the individual cell where it finds the particular receptor and where it binds. Okay. So here also I said so many times different pharmaceutical drug molecule it interact differently. So for example, like there are so many water soluble drugs. For example, this drug for hypertension or something, they prescribe a compound called as atenolol, which actually stays within the blood and the fluid that surrounds the cell. Whereas there are some other drugs related to some anti-anxiety or something, this flurazepate. So these are fat soluble drugs. So they are not going to stay into the blood. They are going to concentrate more into the fatty tissues. So depending on whether a particular compound is hydrophilic or whether it is hydrophobic, it is going to find the thing like where it is going to spend more of its time, and then it is going to slowly move towards binding the particular receptor. So there are so many other drugs which, depending on their characteristics, they are going to be concentrated in some part of your body. For example, if you take an example of iodine, so iodine normally concentrates in the thyroid gland, because you can consider that the tissues, whatever are there in the thyroid gland, they are going to have the special affinity for that iodine. So iodine is mainly going to get concentrated into the thyroid gland. So in the same way, the pharmaceutical drugs also will go and find the particular uh, tissues where they are going to have the most affinity. So I said when this distribution happens, so once it identifies the particular tissues and the cell, then the job of the pharmaceutical drug is that it should go and cross the particular cell so that it can have its activity. So you can consider that I mentioned using these some structures called as this um, phospholipids which are having like surfactant 2 tests, they form this kind of bilayer sheet. So depending on the drug nature, whether it is a fat soluble compound or whether it is a water soluble compound, it takes time for it to cross this cell membrane, which is an important thing. So for example, if I consider this antibiotic rifampin, it is a very highly fat soluble drug. So they say it rapidly enters the brain by crossing some barriers like these. Whereas the pharmaceutical compounds like penicillin, which is a water soluble drug, they cannot easily penetrate these particular types of layer. So in those cases, you need to have some other strategies. Like suppose I said there are some pharmaceutical compounds which you identify through your technique that it is a good candidate for the activity in some part of the brain. And there are some barriers within your body which doesn't allow certain compounds to cross. Like for example, there is something called as blood-brain barrier, where actually only through this barrier to pass through the to the brain, only some kind of hydrophobic compounds are only allowed, whereas hydrophilic compounds they will not be allowed to cross through the membrane. But through your techniques, you have found out that whatever compound you have developed, it is actually hydrophilic in nature, and you want to this compound to cross through these types of blood-brain barrier. So people have some strategies. Like for example, here some example is shown for Trojan horse. Have you heard this name Trojan anytime? What is it related to? Okay, so you can consider, I said, so many times you have different compounds and you need to cross them certain barriers within your body, and they are not able to do that. So many times people utilize some different approaches, like they use some kind of tricks. Okay, so you can consider this Trojan horse. If you read this description, they say like Greeks had the fights with these Trojans, and the fight was going on for more than 10 years, and there was no result. So what finally Greeks pretended, they constructed a huge wooden horse, and they had some of their people within the horse, and they pretended it to the Trojans that they have like accepted their defeat or something, and they have considered like just take this horse as the victory trophy. So means their people hid under the Greeks hid under this horse, and with the night time when they thought that Trojans thought that the Greek forces have gone, so then during the night time when Trojans were not aware, these Greeks came out and they finally destroyed the city of Troy. You might have seen this movie called Troy, and they ended the war. So there is this concept of some kind of tricking has to be done when certain times some molecules cannot pass through certain barriers. So sometimes I said to cross certain barriers, tricks such as Trojan horses are used so that you can deliver certain water or fat insoluble drugs into particular part of the body. There are so many research papers which actually people try to utilize as drug delivery approaches when they want to treat so many of these diseases like Parkinson's disease, Alzheimer's disease. They are trying to utilize this kind of tricks. Then when this distribution occurs, uh, you can consider that some of the pharmaceutical drugs, they are going to leave the tissues very slowly, whereas some like yeah, when they release slowly, you can consider even if some person stop taking the pharmaceutical drugs, then also after the for so many days the drugs will be continuously getting released. So this is also an important aspect in distribution. You can consider particularly in relevance to the vitamins. Like vitamins are really important for your body, and for example, there are some water soluble vitamins like vitamin B12, and there are some fat soluble vitamins like vitamin D. So you can consider when you take any vitamins like B12 or vitamin C, which are water soluble. So these kind of vitamins, they easily get discharged from daily. Like you, even if some extra concentration also happens, these kind of vitamins, they are not holded into your body for the longer time. But vitamins like vitamin D, which is normally produced when you are in contact with the sunlight, so these kind of vitamins get produced. So if you have, suppose if you take it externally, if you have any deficiency, so these kind of vitamins, because as they are fat soluble, so they remain within your body for up to 2 to 3 months. So these kind of vitamins, for their higher doses or something, you can consider they can become more toxic to your body if you are going to take the higher doses of these in a very short amount of time, because they are going to remain within the bloodstream. So these same things is important for the pharmaceutical compounds, like what amount of concentration of doses or something should be taken. This is also dependent on their nature of their hydrophilic or hydrophobic weight. The same distribution you can consider. I know these things are slightly some different things, but just try to get hold on that we are just trying to understand what exactly happens to the pharmaceutical compounds within, and how for different scenario different effects can happen. So in the same way, I said like the distribution can vary from person to person. Like when you are having some like obese people, so they are going to store a large amount of fat soluble drugs. So when some drugs are prescribed for obese people, so it might be prescribed in some other way. Whereas if very thin people are there, so they might store very little. Same way, if there are older people, even though they are thin, they can store a large amount of fat soluble drugs. As you can consider that the proportion of body fat will increase as they will age. Okay, so this is the second distribution state. Then the third step is metabolism. You can consider that whatever drug it will be taken inside, that will be ultimately broken down or metabolized. If the drug is very simple, it is not going to have much changes, but most of the time, whatever these pharmaceutical compounds, you might think that they are too hydrophobic, some of them might not be suitable for your body, or they might be having some toxicity. So you can consider they are eventually broken down into some smaller compounds. They are metabolized using your body's chemical processing plant liver, where these all the compounds, they are cut apart, they are transformed into so many simple things, that so that the excretion should become easier. So there are some details of biology, like which particular enzymes they do all this metabolism. So most of the time you can consider what are these pharmaceutical compounds I said are lipophilic. They are eventually converted into some water soluble compounds so that they can be excreted out easily. So that's why you can consider something complex, you are always converting into something simple. So liver, it is called as the detoxifying organ, which is reducing it to somewhat less toxic compound. But when the metabolism is happening, you can consider there is one more aspect, that there is some chemical alteration. Now, so many times some pharmaceutical compounds you take and you want it to be active for till it reaches the particular part of the body. But what happens as soon as you take it into the bloodstream, it starts interacting with some of the enzymes in the blood and other things, so that before it reaches to the final receptor, the concentration or of that drug or something, it will become very less. So there is, in this metabolism, this is also used as some trick. they use some compounds called as prodrugs. So these prodrugs you can consider when they will be injected in the inactive form. So they will not be interacting with what the active component should is going to interact with the blood proteins or something within a body. It will be initially injected in the inactive form, but eventually it will be altered in the liver. It will be metabolized into the liver, and then this inactive form will be converted into an active form, and this active form will be having its desired therapeutic effects, the medicinal effect. The inactive form you can consider you have initially given to the body, which is not at all active, but in the process of metabolism, this is going to get converted into some simpler form and it is going to become active. So this is going to be important for your therapeutic effect. Then the last step here is the excretion, like whatever you have taken inside the body, ultimately it should eliminate from the body. It is not like it is going to stay within the body. So you can consider that many of the drug molecules, they simply get eliminated from the urine, but some of the pharmaceutical drugs, they can have as the more complex form as the excretion through your liver secretion or in the form of feces. And surprisingly, you can consider like some of the drug molecules, they are also excreted in the form of saliva, sweat, breast milk, or even some exhaled hair. You can consider all the different ways they have for excretion. And these things are particularly important when people are having some kidney or liver problems. So you can consider if they are taking these drugs like a normal people, so their liver, as it is not working properly, so their the high dose can cause toxicity to such patients. So when you are monitoring a particular when you are going to prescribe some drug for a particular people having the liver problem, so they need to given the somewhat smaller doses so that to reduce the problem of the toxicity. So all these factors, just I went into too much biological stuff. I can guess it is somewhat new to you people. But just consider that there are so many of the things what people before deciding which molecular descriptors to choose for the QSA and modeling, you have to have some idea about all these processes. Okay. If there are any questions, you can ask.